So the next thing we want to talk about is the integrations of 1 over u du. Given the derivative result of ln u differentiate with respect to u, I have 1 over u du dx. And to ease my notation, I'll call y as ln u. Therefore, I have dy dx as 1 over u du dx. So what I'm going to do is to take the indefinite integration on both sides. I am looking at this expression and I take the definite integration on both sides with respect to the variable of dx. So I'm going to slot in this expression into my indefinite integral symbol. And I'm going to also slot this expression into the indefinite integrations of my symbol. And when I do that, I assume that the u of x is positive. I'm looking at the left-hand side. This product of dy dx is nothing but just the differential of dy. And on the right-hand side, the product of du dx with dx is just the differential of du. So I have this relationship. And what is this? This is referring to the antiderivative of the constant of 1. So the left-hand side with the indefinite integral sign of 1 with respect to y is just y plus the constant c. The antiderivative that's represented by the integral sign with respect to y is just y plus c. So y plus c is then equals to the integrations of 1 over u. Here, I rewrite this as saying that if I have u raised to the power of minus 1 and integrate it with respect to u, then I'll obtain y plus c, where y is the log of u plus c. And here, u is assumed to be a function that is always positive. That is necessary for u to be defined as positive because the log of u is only defined for u that is positive. If you have a situation where u is negative, you can also arrive at the similar situation where you just have to slot in the absolute values of f. So if you follow the argument on the right hand side of this slide, then you will equally be able to arrive at the conclusion that finally the integrations of u raised to the power of minus 1, it would be just equals to the log of the absolute values of u plus c for any values of u that is a function of x. Now this is an special case where the u is raised to the power of n if n equals to minus 1. If you recall all the formula that we have discussed earlier on, we have actually derived this very simple relationship in the previous lecture that says if u is raised to the power of n and you integrate with respect to u, then you will get u power n plus 1 over n plus 1 plus a constant for u to be any arbitrary function of x. However, this result is only true if n is not equals to minus 1. When n is equals to minus 1, then you have this result that is derived based on the definitions of the natural log. Once you have this very simple relationship, then you can proceed further a little bit. Let the function u to be expressed in terms of gx. Then when you take the differential of u, that is du dx times dx. So this is the definition of the differential. So here you have du dx, and express u in terms of g, you have this dg dx. It's just a change of notation from u to g. And then we write this as g prime of x dx, where g prime of x is just dg dx. So with this, the expressions of du over u would then be expressed into the form of g prime x dx. So here you have g prime x dx, and downstairs u is now replaced by the expression of gx, and that is equals to log of absolute values of the g of x plus c. Here g of x is just the u, and the g of x must be sitting inside the absolute value. If you have an integration in the form of the ratio of the differentiation of the function divided by the function itself, and you integrate over the variable x, this indefinite integration is just simply equals to the log of the absolute values of the function g plus c. A very simple example could be seen from here. Example 4. So here you have these integrations in the form of the ratio of 2x, x squared plus 5, and you integrate it with respect to x. This is a typical example of integration that is in the form of g prime x over gx. Anytime when you can express and integrations into the form of the ratio of the derivative divided by the original function, then you can easily write down the result of the integration in the absolute of the logarithm. So here it is understood that 2x is just the derivative of the function x squared plus 5. In order to see these things clearer, you can always call the function gx downstairs as x squared plus 5. Then when you take the derivative, you got 2x. Therefore, this is then 2x over x squared plus 5 can then be expressed into the form of g prime over g of x dx. Then the answer is just the log of the absolute values of g of x, which is x squared plus 5. And also, you don't forget the constant c. Now, since x squared plus 5 is always larger than 0, then it doesn't matter if you throw away the absolute sign, because the function is always positive with or without the absolute sign. You can perform another definite integrations of 4 cos x over 3 plus 2 sine. In example B, the integrand function is a ratio of two functions. After some consideration, you can actually see that the numerator in the function is in the form of the derivative of the function in the denominator. So to see this clearer, let us define the function in the denominator as 3 plus 2 sine x, so that well, sometimes you call this u, sometimes you call this g. It doesn't really matter. Okay, I'll call this g, so that g prime of x is just then equals to 2 cos x. So that 2g prime is just equals to 4 cos x. 2g prime is dg dx is equals to 4 cos x. Then I'm going to multiply the dx on both sides. After this very simple transformation, then you can see that 4 cos x dx is just 2dg, because the right hand side here, the product of dg dx times dx give me the differential the expressions of 4 cos x dx is now replaced by 2 times dg over g. This would then be simply equals to 2 times log of g plus a constant. And then this is just equals to 2 times log of g here is defined to be 3 plus 2 sine x plus c. So that is the solution to the indefinite integrations of 4 cos x over 3 plus sine x. But the question is requiring a little bit more. The question asks me for the definite integration instead of the indefinite integration. So what I have found until this time is the indefinite integration, that is 2 times log of 3 plus sine x, and it has to be in the argument of log has to be in the absolute sign plus and c prime. So if I were to calculate this based on these x from minus pi over 2 to pi over 2, then this is then I have to evaluate this between pi over 2 and minus pi over 2. So that could be easily calculated to be just 2 times the log of sine plus 3 plus sine of pi over 2 minus the log of the absolute value of 3 plus, here is a 2, sine, and then I close the square bracket. Now sine of pi over 2 is sine 90, which is 1. Sine minus negative 90 is minus 1. Complete my calculation to be 3 plus 2 times 1, which is 2, minus the log of absolute values of this number, where this number is just simply equals to 3 minus 2. And yeah, it's minus 2. So that will give me equals to 1. So I have the log of 1. And log of 1 is just simply equals to 0. So after this, I write down this to be 2 times log of absolute values of 5, which is 5. So this is my result, 2 times log of 25. So that is the result I obtained. And to make sure that I am doing this correct, I would like to check the solutions using Wolfram Alpha. So when I check it against Wolfram Alpha, the integrations or the definite integrations is log of 25, which is exactly equals to the value that I have just calculated. The next example I want to talk about is the integration of tangent x and cotangent x. The cotangent x has an antiderivative which is equals to the log of sine x. You can derive the antiderivative for cotangent x using the formula of du over u following the procedure here. You define the cotangent x as the ratio of cos x over sine x, and you call u to be sine x. Then the antiderivative of cotangent x is then just expressed as u and du, where the u is sine x du. From here we can easily work it out to be cos x dx. The du is the differential of u, so this is then easily expressed as the absolute values of u, which is log of absolute values of sine x plus c. So that is the derivations of the antiderivative of cotangent x. Using a similar tricks, you can also easily arrive at the result for the antiderivative of tangent x, which is sine of x over cos of x. So that is the definitions of tangent x equals to sine x over cos x. So in this case, you call u to be cos x, then du is minus sine x dx. So here, this sine x dx is just simply equals to minus du over u, because the du carries a minus sign with respect to sine x dx. Therefore, replacing sine x dx by minus du, you can express the integrations of sine x over cos x into the forms of du over u. That would just give you minus ln of u plus c, which is just minus ln of cos x plus c. And if you want to simplify this further, you can make this as the cos of x raised to the power of 1 in absolute sign, and 1 over cos of x is just cosecant of x, secant, not cosecant, secant of x in the absolute sign plus nc. So that finished up the derivations of the integrals of tangent x and cotangent x. So you can easily perform the integrations of tangent x using the formula used here, where you just substitute tangent 2x by tangent u, and you call u equals to 2x.